Welcome to today's lesson on nomenclature. Nomenclature is just naming. Okay, so we're going to focus on naming compounds, specifically today binary compounds. So ionic, covalent. We talked about what those were. So quickly, just to review, if I'm talking about an ionic compound, I'm talking about a metal bonded to a non-metal. Okay, and if I'm talking covalent, I'm talking about two nonmetals. So non-metal plus non-metal. So looking back, starting with ionic compounds, we're going to be dealing with metals and nonmetals. And what you're always going to see in an ionic bond is the metal providing an electron to the nonmetal. So if you remember, the metals, we're looking at our periodic table, we'll find mostly here on the left-hand side of the periodic table. Okay? And on the right-hand side, we'll find our nonmetals. Generally, since you're looking at these first two or three columns in the periodic table, you're dealing with atoms with a lower number of valence electrons. For example, the first column all have one valence electron. Things like lithium, sodium, potassium, hydrogen. The second column, beryllium, magnesium, calcium, strontium, all have two valence electrons. Okay, so they're looking to give those electrons up. When that happens, they have a positive oxidation state. Okay, now they're most likely going to bond with these nonmetals here on the right. Things like fluorine, chlorine, bromine, oxygen, sulfur. Okay, so if you're looking at that seventh column, fluorine, chlorine, bromine, iodine, they have 7 valence electrons, so they're looking to get one more electron to fill that valence shell. Okay, again, column 6, oxygen, sulfur, selenium. These have 2 or 6 valence electrons, so they're looking to gain 2 electrons. And when they gain electrons, they become negative. Right? So oxygen would gain 2 electrons. It's going to have 2 more electrons than it has protons, so it gains a negative oxidation state. So for example, when something like sodium bonds with something like oxygen, sodium starts with that 1 valence electron, and oxygen starts with 6. Okay, so oxygen, you see, is looking for 2 valence electrons. Okay, so it needs 2 more electrons to be happy. Sodium has 1 to give up. So what you end up seeing here is you need an extra sodium for this bond to work. Okay, so sodium gives up an electron, and you need 2 of them to fill your 2 oxygen, or your 2 empty empty spots for oxygen. So you end up with 2 sodium 1 pluses and 1 oxygen 2 minus. All right, so now everybody's happy. So when that happens now, you've got these very strong positive charges and this very strong negative charge, which are strongly attracted. So now, how do we name this? So that's the actual bond, and again, we'll continue to study this and go deeper into why these things are happening and how. But how do we name this? So looking at ionic compounds, let's go from a name to a formula. Okay, so the first thing you would do is write the symbol of each element in the formula name. So let's just use the example that I just gave you of sodium oxide. Okay, so I'm going from the name, and now I want to get down to a formula. So the first thing I will do, I'll write the symbol of each element in the formula name. Sodium and oxygen. Now I'm going to write the charges of each ion above the respective symbol. So if you remember sodium from the periodic table, it's in this first column. So we know it has 1 valence electron, so it's going to have a charge of 1 plus. Oxygen, on the other hand, is in the 6th column, so we know it's going to have a 2 minus charge. Right? And now my last step here is to cross the numbers without the signs. So this is what we call the cross rule. Okay, and so I'm just going to cross these charges down, and so now I end up with Na2O. And we saw that as when I showed that example. Okay, so this, you can see where this comes from now. I have 1 valence electron in my sodium, I have 2 open spots, so I need 2 sodiums to fill, or I need 2 electrons from 2 separate sodiums to fill the 2 empty spots in that 1 oxygen. So this is where that ratio comes from, and this is where that cross rule comes in very handy. Okay, so we're just crossing them down, we're getting rid of the charges. You may see an example, something like magnesium carbide, where you're starting with a 2 plus and a 4 minus. When you cross, you end up with Mg4C2. In a case like this, we're going to reduce, because if you remember, ionic compounds are lattices, okay, and we're talking about units, so we can reduce something like this down to its lowest possible unit. Sodium oxide, we can see, is already reduced. You can't reduce that anymore. There's no common factor to divide by. So this one stays as Na2O. But magnesium carbide, we do reduce down to Mg2C. Okay? Now in reverse, we need to do the opposite. So let's talk about going from formula to name. So another option that we can look at, let's use magnesium chloride. Okay? So I'm going to start with the formula. I now need to get down to the name. So the first thing I'm going to do, I'm going to write the full name of the first element. Magnesium Mg. And then I'm going to write the first syllable of the second element. So this is chlorine, so I'm going to write chlor. And I'm going to drop the ending and add ide. So it just becomes magnesium chloride. And you see that with our sodium oxide, right? It was sodium and oxygen, it becomes sodium oxide. Magnesium and carbon become magnesium carbide. Okay? And again, we're expressing in lowest terms. Now, how do covalent binary compounds differ? Again, we're dealing now with nonmetals bonding with nonmetals, and they're sharing electrons. And we'll talk, again, we're going to go into more depth as we continue to study these compounds. But let's go from name to formula. So we've got a name like something like carbon dioxide, very common. So in this case, when we're going from name to formula, we're going to start by writing the symbol of the first element. So carbon is just C, followed by the number of atoms present as indicated by the prefix. Okay, so if we scroll down here, we've got all these prefixes. I have one carbon, so I have no prefix in front of carbon. So in this case, when I'm leading the first word, if it does not have a prefix, I assume it's a mono. So carbon, mono, I have no number here because it's a 1. Okay. My next step here is now to write the symbol of the second element. So I have dioxide, which I'm looking here as I see the oxide, it must be oxygen. So I'm going to write my O, and followed by the number of atoms present as indicated by the prefix. So now I see di. I have di must be 2, so I can put a 2. Okay. So now let's go from formula to name. Okay. So I'm going to start with a formula something like this. My first step is to write the prefix for the number of atoms of the first element. So I have 1I. Clearly here I have no number beside my I, which means I have one of them. Right? So this is mono, but since it's beginning, if there's only one atom, the prefix mono is not needed. Okay? So then I'm just going to write the full name of the first element. So I'm going to start with iodine. Okay? My next step is to write the prefix for the number of atoms of the second element. So now I have chlorine here, and I have 5 of them, which is penta. So I'm going to write penta. And again, I see this is chlorine, so just like I did with ionic compounds, I'm just going to write the first syllable, chlor, and end with ide. Okay, so really the big difference here is we're adding the prefix on these compounds. And the reason for that is, with our ionic compounds, we can predict how many of each atom there are based on the charges. We cannot do that with a covalent compound. Because of the sharing, there are many different options, there are many different possibilities in a lot of cases for the number of each atom present. And so we need to indicate which compound that we're dealing with by using these prefixes. Okay? So the simplest formula indicates the simplest ratio by which atoms or ions combine in a compound. If the ratio is correct, then the total sum of the positive oxidation and the total negative oxidation of the compound will add up to the net charge on the compound. Right? So since silicon sulfide is neutral, the net charge on silicon disulfide is 0. So in this case, silicon has a 4 plus charge and sulfur has a 2 minus charge, but we have 2 of them. So again, we can see 2 times 2 gives us our 4, and that cancels out my 4 positives. Okay, so this is a nice way to check, certainly on ionic compounds, when you're dealing with the positive and negative oxidation states, whether this is going to be a neutral compound or not. And we'll get into our covalent compounds and how you can do some checking a little bit later. But again, when writing those formulas, you're given how many of each thing there are in the name. You're just looking for prefixes. Whereas in the case of ionic compounds, it can be a little trickier. So you can always check by using these oxidation states, multiplying the oxidation number by the number of them, and in each case, see if they cancel each other out. In this case, they do. I must have a neutral compound. Okay, 2 more things just to quickly touch on. Diatomic gases. Okay, so anything, so basically if you're talking about hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine, they do not travel by themselves. Okay, so if you look at the periodic table, most metals, if they're not bonded with anything, they're okay to be by themselves. They will bond to each other in what we call metallic bonds. Okay, but these these gases over here, not noble gases, but these nonmetals, they tend to travel as a pair. Okay, so you'll never see an oxygen by itself. If it's not if it's not bonded to another atom, you'll have it bonded to itself. Okay, fluorine, chlorine, bromine, the same kind of thing. And you'll find that they're all kind of up here in this corner. Okay, that sort of staircase, sulfur's a part of that as well. Okay, so these are all called diatomic gases. You're not going to see them by themselves. And last but not least, we have the noble gases: helium, neon, argon, krypton, xenon, and radon. So they are monatomic gases because they're already happy, right? They have their full octet. They have those 8 electrons in their outer shell, and so we're not worried. They're not worried. They're not looking for any electrons. They're not looking to get rid of any electrons. Okay, so they have a full shell. They just travel alone. Whereas this elbow here, basically from nitrogen down to iodine, they're diatomic gases. Okay. They will always travel in pairs. This one will always travel alone. Okay. Thank you, gentlemen. Good luck with